So we'll just give it another 2 minutes and then we'll start. Thank you.
Hey, Ali.
Hi, everybody. There is a jet flying over, so that's why
No worries.
I put it on the mute.
Enjoy them. They're not flying very often these days.
And Chasm, just quickly, if you want to check the share settings, just to make sure Shibo has the settings,
I'll do that.
or you can make him co-host, up to you. But
Sure. Thank you.
or. Yep, no problem.
Okay, we have 17 people. I'm just going to start through the introduction of slides. Good morning, good afternoon, and good evening, everyone. It's great to see you in our first Engineers Life event. So what I'm going to do, I'm just going to go through our introduction of slides very quickly. Most of you are already familiar with this. So this event is part of our SAMPE Canada student chapter activities, and our student chapter is sponsored by the professional chapter. So Jordan here is our chapter president, and myself, I'm the faculty advisor. You can see our email addresses if you want at any point to be in touch. We have a lot of help from our great executive members. So we have Peter, Richard, Claude, Barry, Edu Rees, and Barry Burnett. And for sure, we always need more help from other professors or students. And our initiatives is the Engineers Life event. So for example, we have for our future events, we have Boeing, Stigma, and other companies that they already confirmed. So if you want to be involved in organizing this event, for sure, just talk to me or to Jordan. And we are looking for a collaboration with the UBC chapter, the student chapter at UBC, to organize one Engineers Life event in the fall. So we are still in discussion, but that will be very interesting. I also wanted to quickly talk about what we want to do. So when we say help from other students, it will be great to have student groups from Canada to go and present or to participate in competitions for SAMPE NA. And there are a lot of interesting competitions, and you can see all that information in SAMPE, nasampe.org. So what I'm going to do, I'm just going to share the website and show to you how easily that can be done. So if you just go to nasampe.org, and then you go to the student, and you can see here contest. So you can collect, and some of these contests are for 2021 or 2022, like the additive manufacturing contest, bridge contest, leadership experience award, student poster contest, SAFE contest, so that's for analytical failure analysis, and research symposium. As a student member, you can go and register for SAMPE 365, and that's also a very interesting networking tool that I'm sure a lot of students will appreciate. So again, all those information are there. You can just go there, click, and you'll see description, videos, all that information. Okay, so by that, I'm just going to go ahead, get back to the presentation and go to the next slide, and I'll pass it to Jordan.
Great. Thank you very much, Chasm, for the introduction. And I'd like to welcome everyone to our Engineer's Life event. As Chasm mentioned, this is our 4th event, and we're happy to have you all here. So as usual, we'll have presentations, some videos, and some lessons learned from our speaker. The time varies sometimes, so today will be around 30 minutes, and we have a PowerPoint presentation, and we have our speaker, which I'll introduce shortly, followed by a poll. This is just to rank the presentation. As a reminder for those who don't know, we are ranking all of our events, and then we'll have a winner based on the polls and our reviewers. So we'll be ranking how you enjoyed the presentation. So that will just be 3 short questions ranking 1 to 5. And that should take a minute or 2. And then we'll have our Q&A period here. So this could be 10 minutes. We can allot a little more time here if needed. So anyone is welcome to unmute and ask Shibo, our presenter, questions at the end. And we have also time for, networking and talking with other attendees. And our reviewers today, we have a professor, and he's R&D technical coordinator at Hutchinson, Dr. Cedric Pupin. So he is joining us today, and we have Chasm as well, our vice chair here from Ryerson. So he will be our other reviewer, and we changed these 2 reviewers throughout. So without further ado, I'd like to welcome our presenter, Shibo Zhu. He is currently in the Netherlands, so he's joining us a little later for his time zone, but we're happy to have him here, and he is a graduate. He did his PhD at Polytechnique. So Shibo, without further ado, we'd love you to share your screen and take it from here.
Perfect. Sorry, Shibo, very quickly. I just wanted to also mention that I'm just going to start, because it's the start of the presentation, start recording the session. And as always, we are not recording the videos, it's just recording the screen. So it's just a PowerPoint presentation. Thank you.
Great, thank you, Chasm. Thank you, Jordan, for the introduction. Hello, everyone. Thank you very much for attending this.
This meeting is being recorded.
My name is Shibo Zhou. It's a great honor for me to present to you some of my PhD work today at this special event organized by SAMPE Canada. In this project, we aim to develop a transparent impact absorbing composite with this sacrificial bonds toughening mechanism. So first, I would like to give you a short introduction of myself. So I'm currently a postdoc researcher at Amhof Institute in the Netherlands, working on soft robotics. Previously, I finished my bachelor degree and my master degree in East China University of Science and Technology in Shanghai. And later, I did my PhD at Polytechnique in Montreal. During my PhD, I also did an 8-month internship in the stress engineering group at Bombardier. There, I was working on a composite project about the buckling analysis of the hybrid stiffened composite panel on the after fuselage of Airbus A220. And today, I'm going to show you my PhD project that has been done at the Laboratory for Multi-Skill Mechanics at Polytechnique Montreal. So this is outline today, because this Engineers Life event series organized by SAMPE Canada focused not only on technical presentation, which is related to composite, but also it aimed to give people a better knowledge of what kind of activities, day-to-day activities that a researcher does in a research institute or a company. So after a brief introduction of the technical project about the composite, I will give you also an introduction of all the activities that we did at Polytechnique Montreal, and what kind of problems and how we fix, what kind of problems that I have during my PhD studies and how we fix it. So why we would like to develop this impact absorbing composite? What's the motivation behind this? So as we all know, all the structure in materials in engineering systems, they have to be not only strong in order to withstand the high mechanical loads, but also they have to be very tough in order to absorb large amount of energy in order to resist fracture and maintain structural integrity. For example, here, the windshield material on the aircraft and the containment material in the turbine engine. In those applications, the material has to be really tough in order to absorb a large amount of kinetic energy, either from a bird strike or from the flying broken turbine blade. So how we can come up with new designs in engineering materials to improve the impact absorbing performance of the material. So our inspiration comes from nature materials, specifically the spider web. So here I'm going to show you a video that I found on YouTube to show you how impressive the energy absorbing capabilities of the spider web are. And as you can see, the title of this video is called Spider versus Frog. It's sounds a little bit horrible. And also the video content that I'm going to show you might be a little bit disturbing for some people, but I assure you that no one got hurt from this thing. And you can see, so even though spider web is not designed to capture large animals like a frog, but you can see how impressive under this huge impact, the spider web is still able to maintain the integrity and finally catch this frog. And by the way, the spider didn't eat the frog in the end, because soon the spider realized that the skin of the frog is toxic. So what happened in the end is that the spider has to cut the spider web around the frog and to release the frog without hurting him at all, without being hurt. So, but anyway, this gives us an idea that the spider web is able to absorb a large amount of energy under impact. And this fascinating behavior has attracted researchers' attention for more than 2 decades. So at first, people try to do mechanical tests on a single silk thread. As you can see here, the false displacement curve of a single silk thread. The area under this loading curve represents the total amount of energy absorbed by the spider silk. And upon unloading, the area under this unloading curve represents the elastic energy that will be released upon unloading. And in between this loading and unloading curve, this is the actual amount of energy that has been dissipated out of the system. It has been found that in spider silk, up to 70% of the total absorbed energy is actually this dissipated energy. And this high energy dissipation is especially beneficial for spider web, because it can significantly reduce the oscillation of spider web during pre-capture. And of course, it can significantly increase the successful chance of pre-capture. And later research found that this high energy dissipation behavior in spider silk is attributed to the silk molecule structures. In the silk molecule, there exists a large amount of sacrificial hydrogen bonds within those entangled protein chains. Under stretching, those hydrogen bonds will be sacrificed, they will be broken, and release those entangled hidden chains that we call hidden lengths. And the breaking of the sacrificial hydrogen bonds and the unfolding of those entangled chains contribute to the high energy dissipation of spider silk. So people always try to implement this sacrificial bonds toughening mechanism into engineering materials, try to achieve this similar high energy dissipation behavior. And there already exists a large amount of study where people at the molecular level, researchers integrate those sacrificial bonds into elastomers or hydrogels, and they achieve significant improvements in terms of toughness and other mechanical properties. In this project, we aim to implement the sacrificial bonds toughening mechanism into the microstructure of the engineering materials and seek to find a new design that probably easy to scale up for large production and industrial applications. So in the literature, there already exists a few examples where people try to make this sacrificial bond structure in the micro or nanostructure of the engineered materials. So the first example shown here, the researcher made a knot along this carbon nanotube microfiber. Under stretching, the hidden length, the length hidden by the knot will be released, and the energy is dissipated by the friction during the releasing of this knot. And this increase a lot of the toughness, the energy absorption of this single fiber. And in the second example here, the researcher tried to introduce the stacked carbon nanofiber into epoxy composite. So the way that if you stretch a single stacked carbon nanofiber, because there exists a weak bonding in between the helical layers. So when you stretch it, the interlayer bonding will be sacrificed, will be broken first, and they will release this hidden length along this fiber. And the researcher also integrate this, add this kind of carbon nanofibers into epoxy materials to make this complete, and they achieved also the improvements in terms of toughness. And in the two examples below here, they use two systems, two networks in the material system. One is the weak component inside as a core or as a reinforcement. And the other one is the weak matrix material as a shell or just as a matrix material. And upon loading, the inner material, the weaker material, will experience sequential breakage, which is similar to the sequential breakage of sacrificial bonds. So in this way, they also achieved improvements of the toughness of the material under static loading conditions. So for 2 decades, people treat the sacrificial bonds toughening mechanism in spatter silk has been regarded as a perfect strategy for shock absorbers. So in our project, we aim to implement this sacrificial bonds toughening mechanism into the engineered materials and to see whether or not we can achieve this high energy dissipation behavior as that in the spatter web. So the technique, the fabrication technique that we used in our group, it all comes from a very simple physical phenomenon called liquid rope cooling. This is when you deposit a viscous thread from a certain head onto a horizontal plane. Due to the compressive stress along the thread, buckling instability will be triggered, and the material will start coiling before touching the ground. And my previous supervisor, my PhD supervisor, Professor Frederick Gosling and Professor Daniel Tahil, they found very similar cooling phenomenon on the FDM 3D printer. And then they further deposit this molten thermoplastic polymer onto a horizontal plane, a moving horizontal plane. As you can imagine, when the extruding speed of the molten polymer is equal to the moving speed of the horizontal plane, we will have a straight fiber, a straight pattern on the plane. But as we slowly decrease this moving speed of the platform, that is when the instability comes to play. We will have different patterns from meandering to alternating and to coiling, and finally the fiber with overlapping loops. And because the material is also cooling down during this deposition process, at the intersections along the fiber, a weakly fused bond will be created. And these weakly fused bonds will actually act as sacrificial bonds upon mechanical loading, as you can see here. Under tension, the sacrificial bonds, they will be broken one by one and release these hidden lengths along the fiber. And this gives us extra peaks on the force displacement curve shown here. And the area under the force displacement curve represents the amount of energy absorbed by the system. And this gives us this toughness enhancement. And we also developed finite elements simulation of this kind of structure. And we found that actually during the unfolding process of the fiber, large-scale plastic deformation was happening along the fiber, and this explains why so basically all the energy dissipation comes from the plastic deformation of the unfolding fiber. So next, our next task is how we can implement this single fiber structure into engineering bulk materials for impact protection applications. So I further developed this instability assisted 3D printing technique to be able to print this bidirectional fiber fabric. And after printing, we manually separated the 2 layers of the fabric and tested them separately under mechanical loading. And we found that the mechanical properties of the the fibers from the two layers, they are pretty similar with each other, except that the bond strength on the second layer is a little bit less than the first layer, but the general behavior is similar. And all the sacrificial bonds, they are all functional in both layers. And later, we developed a resin injection system using a syringe pump to inject a transparent elastomer resin around this fiber fabric. And in this project, we used two different elastomers. The one, so the refractive index of our fiber fabric, the polycarbonate fiber fabric, is around 1.58. And we use two elastomers with different refractive index. One is much lower than the PC fiber, which is around 1.41. And the second one is a high elastomer with a higher refractive index, which is around 1.55. This one is much closer to the PC fiber. So that's why I can see with the better matching on the refractive index, the fiber almost disappear in the resin, and this gives us a better transparency. So we also did optical test on these two kinds of composite based on different elastomers with different refractive indexes. So it shows that the optical transmittance of both the composite is around 90%. So it has high transmittance. So we also want to know that how the difference in the refractive index between the matrix material and the fiber, how this difference will influence the scattering properties of the material. So as you can see here, this is schematic of the optical test that we did. So as the incident light transmits through the material, the total transmittance actually includes two components. One is the specular components, and the other one is the diffuse components. So we can define haze as the ratio between the diffuse components over the total transmittance. So this gives us a better idea of how much light was scattered by the composite film. So as you can see here, in the high RI elastomer-based composite, in which the refractive index of the matrix material is much closer to the fiber itself. So in this composite specimen, we have the haze, almost half of the haze with the low RI elastomer, in which the difference between the matrix refractive index and the fiber's refractive index is much higher. So in the end, we finally tested the impact absorbing behavior of our composite on a falling dart impact tester. So here we use a drop head of around 0.9 meter, and the drop weight is a little bit more than half a kilo. So this gives us an impact velocity of around 4.2 meter per second and the impact energy around 5 joule. And we also use a high-speed camera to capture this. And we test 4 different specimens. The pure elastomer resin, pure elastomer film, and the one reinforced by straight fiber fabric, and the 2 other specimens reinforced by the sacrificial bonds-based fibers. So as you can see here, in the meantime, we were also able to measure the impact force and the impact displacement. So as you can see here, the falling dart penetrates both the control specimens, and it was successfully caught by the sacrificial bonds-based composite specimens. And as you can see here, the spring back of the falling dart, this enabled us to measure this unloading curve on the impact force displacement curve here. And with this unloading curve, we were able to calculate how much energy was released, what's the amount of elastic energy that is released upon unloading, and how much energy was actually dissipated out of the material during this impact. And this way we were able to calculate the hysteresis, which is the ratio of the dissipated energy over the total amount of energy. And we found that actually during the impact, up to 95% of the total absorbed energy was actually dissipated out of the material. And this proves that we are able to implement the sacrificial bonds toughening mechanism in engineering materials and achieve this high energy dissipation behavior, which is similar to the spider web. So this work has been published on Cell Reports Physical Science last year in November. So this is the technical part of this today's presentation. So next, I'm going to show you how we did this project at the LM2 lab at Polytechnic Montreal. So first, for those of you who don't know where is Polytechnic Montreal, here is a brief introduction. So it's in Montreal. Of course, you can see the Olympic Stadium here. So Polytechnic Montreal is affiliated to University of Montreal. So here, the tall building here, they belong to University of Montreal. And this 3 building here is Polytechnic Montreal. And I was working at the laboratory for multi-skill mechanics in the Department of Mechanical Engineering. And this group, the laboratory was led by 3 professors. Professor Frederick Gosselin, whose expertise is in cylinder structure mechanics. Professor Daniel Tahill, whose expertise is in additive manufacturing. And Professor Magdan Levesque, whose expertise is in multi-skill mechanics. And the research in the lab focused on metal, polymers, and composites, and living matters. Currently, there are 3 research associates, 9 postdoc, 26 PhD, and 19 master students in the lab. So it's pretty big. And considering the research facilities, we have 2 labs within Polytechnic Montreal. So one is the additive manufacturing lab, which is at the 5th floor of the GRB building. And basically, in this lab, we have different additive manufacturing equipment, from low-end FDM 3D printer to a high-end robotic arm, which is we also mount different kinds of printer head onto this robotic arm in order to print on complex structures. And we also have a bunch of directed write 3D printer and also industrial level AON 3D printer, which enable us to print high performance peak thermoplastic composites. And the 3D printer that I was using is actually a very simple one. It's a Prusa 3D printer. You see here is a wooden 3D printer, but the extruder that I was used is a high-end extruder developed by a local company in Montreal called Dice Design. And people may question that because the price of the extruder sets is even more expensive than the printer itself. It is because that in this project, the extrusion, we want like a perfect stable deposition, so that we can make a high quality fiber fabric in this project. And also there's another lab which in the main building, the first floor of the main building, where we have different kind of electromechanical testing machine or a hydromechanical testing machine within this lab. And also during my PhD project, I was constantly using this electromechanical testing machine called MTS Inset. So in order to give you a better idea of what's the daily activities that we did that I did during my PhD, here I'm using this one episode from a scientific television show from Radio Canada called Découverte. Earlier this year in January, they came into our lab to shoot one episode to introduce our impact absorbing composite. So with this, by using this video, I'm going to show you what's the activities that are done in the lab. So this is the additive manufacturing lab that I have previously mentioned. We have AR 3D printer and also a bunch of direct-to-write 3D printer and a mixture because we are doing 3D printing, especially for the direct-to-write 3D printing. We have to mix the ink. We use different mixing technologies. So we have a lot of bunch of mixer here. So this is my supervisor, Professor Frederick Gosselin. So basically, I was using this Prusa 3D printer here. So this is more like, so I would spend 1 week or even 2 weeks just to prepare the fiber specimen. And as I also already mentioned, the extruder set here is more expensive than the printer itself, because this way we can have a stable deposition. We can ensure that the deposition is quite stable. But because the 3D printer is quite cheap, so I encountered, so during my PhD, I think this is also normal for every PhD student. So sometimes our equipment broken, like this 3D printer, I have to spend a couple of weeks to fix this 3D printer because it was always missing steps. And later I found out that it's because of the driver for the stepper motor is not compatible with the power source. It sounds silly, but that's the reason. So, but even though I spent a couple of weeks fixing the machine, but this helped me to understand better the 3D printer. And this actually, the knowledge that I obtained during the repair of this machine is actually helping my postdoc research right now, because currently I'm 3D printing silicon for soft robotic applications. And those knowledge is extremely helpful for my current project. And then so as you can see here, the printing, it might look very smooth here in the video, but actually I have to spend a lot of time behind this to tune the machine, because sometimes the material gets stuck inside the nozzle, or the PID control, the temperature control was easily affected by some cable malfunctionality, and then I will have very bad deposition, and the fiber pattern doesn't look good at all. So this means that actually for a PhD student, we have to work really hard in order to get this kind of satisfaction. When everything is working really well, we can produce our results and to show people and to make meaningful results for real applications. And the next step is the composite. In order to make the composite, also because the fabric and the resin that we used is is not conventional in the manufacturing. Like epoxy is very different from epoxy-based composite because it's kind of soft. So I also have to develop this resin injection system using a syringe pump and also using a laser cutter to make the mold. And this way we are able to inject the resin around the fabric without producing any bubbles. And also we can also control the thickness, control the thickness of the composite. And also there are other skills that are involved during my PhD, I think during every PhD students. And so during their studies, and that is the project management. For example, here, as I mentioned, I was using 2 different elastomers with different refractive index. The one with higher refractive index actually is quite expensive. Every time, actually, it's produced in the factory in Japan, and the shipping usually takes like 6 months. So at the time that I ordered this elastomer, actually I made a mistake. That's the one thing that I wish that I knew during my PhD, so I can save time. So after ordering the high refractive index elastomer, I thought that because I have to wait 6 months, so I thought maybe I can try to synthesize the elastomer myself. So I investigated a lot of time to do the chemical synthesis of the high refractive index elastomer, because I found some literature for they were able to synthesize this elastomer with a high refractive index, which is exactly the same, which is very similar to my PC fiber, and that's exactly what I want. So I followed their protocol to make this. But actually, in the end, even though I was able to produce a high refractive index in the elastomer, but the process is actually not scalable at all. I can only make the elastomer with the thickness of a few microns, and it's impossible to use that method to make the bulk engineering to make the elastomer resin to form my composite. So I basically, while waiting for the elastomer, I was I would have been able to actually continue the project without using the high refractive index elastomers, just use normal elastomer, and to develop and also invest time on building up the impact tester and design and carry out all different kind of impact tests. But it already happened. So that's the lesson that I wish I knew before the end of my PhD project. And of course, yes, and last I'm going to show you the impact tester that we have in our lab. So because, and also the story behind this impact tester, because the material that we developed, actually, according to my calculation, is the impact force should be around below 200 Newton. But actually, the only available impact testing machine in our department, it has a load cell of a few above 10,000 Newton. So it's way higher from my composite. So I couldn't use that impact tester. So I had, with the help of the technicians from Benedict and Yannick from our department, we were able to make our own falling dart impact tester. And this way we can design our own fixture. And the way that we did it is we assembled a force sensor, a very cheap force sensor of below 100 Canadian dollars. And we put inside this falling dart. Whenever the dart is at rest, there will be no force. And whenever the dart hits on the specimen, we can detect the force with a very high data acquisition frequency, up to 7,000 data points per second. And this way, we were able to measure the impact absorbing capabilities of our materials. And of course, the work was done with the collaboration between technicians and my colleagues, and also the supervision of my professors. And so to summarize, in this project, we were able to implement the sacrificial bond toughening mechanism into engineered materials and achieve this high energy dissipation behavior, which is similar to this energy dissipation behavior in spider web. And what will be interesting to do next is to integrate this impact absorbing film in laminated glasses or other laminated plates to improve the energy dissipation of the engineering structures. And another interesting direction is also to integrate our impact absorbing composite with the currently developed nature-inspired architecture ceramic plates to use at an interlayer between those architectural plates to further increase the energy dissipation behavior. So this finished today's presentation. So I would like to thank Professor Eduardo Ruiz and Professor Kazem Fayaz-Bakash for the invitation, and also I would like to thank Jordan for all the organization. And of course, for my PhD, I would like to thank my supervisor and my colleagues at the IRM too. And thank you. And I will be happy if you have any questions.
Thank you, Shibuzu. It was a great presentation. I really enjoyed it. I'm sure that was the same for the rest of the audience. So what we're going to do, and you saw that in the introduction slide, we're just launching a poll. There are only 3 questions. They're very simple. So if you please answer those, and then we'll go to the Q&A period. So I'm just launching the poll right now.
Yeah.
Perfect. So far I have 78%. I'll just give it another 30 seconds. Okay, perfect. We have 100% participation. Thank you for the polls. This is great. So what we can do right now, we can just go directly to the Q&A period. So are there any questions for Shibu? What you can do is you can just raise your hand and then I'll just call you. You can use the reactions feature in Zoom. So perfect. Cedric, go ahead.
Yes. Hi, everyone. Hi, Shibo. Thank you for this pretty interesting presentation. I've got a question for you. I think that 3D printing is a pretty slow process in general. Do you think it can be suitable for high volume production or the kind of application that you see in the future? Do you think that economically it's going to be suitable due to the very slow rate of the 3D printing compared to other process that we can use for these applications?
Yes, thank you, Strick, for the question. Yes, you're right. Normally, the FDM 3D printer is quite slow if we want to create bulk engineered materials with complex structures. But the methodology that we use here, we use the instability of the molten polymer thread to create this fiber fabric. Actually, the deposition process is quite quick because in order to create this kind of complex structure, we don't manipulate the extruder to go with exactly the path of the fiber to create this complex structure. We just ask the extruder to move along one straight line, and by manipulating the velocity difference between the extruding speed and the moving speed, we were able to create this kind of structure by just taking advantage of the instability of the molten polymer. And actually, this process is quite fast. If we can get everything all right, everything stable, and we can produce large-scale plastic fabric very fast. And I think this won't be a problem for large production. But there's one thing that I think which could be a problem is that because here I'm still printing this fabric at a much larger scale, at millimeter scale, but it will be interesting that if we can make it even smaller, like with a size maybe a few microns, and that maybe can slow down the fabrication process a little bit.
Perfect. We also have questions under the chat. So Peter, that's a question from Peter. What do you see as the best application for this technology?
Okay. Yes. When I wrote the thesis, I wrote that I would like to use this on the sports protection, like a helmet or something. And then the professor during my defense said that because the material actually here, the thickness of my material is about 1.5 millimeter. And actually, during impact, the displacements can go to 60 millimeter, which is like 30 times of the thickness of the material. And if we want to put it on the helmet, the brain will be smashed under this impact. And then that reminds me that maybe there's another interesting application, which could be space debris capture. So in the space, there exists a large amount of spray which goes at a very, very high velocity. And currently there doesn't exist many effective strategies to catch those sprays and remove them, clean them. I think this kind of composite design, the material design, to use the sacrificial bonds in the engineered materials, it could be possibly used to catch those space debris.
Perfect. Thank you. So next, under the chat from Ridwan, thank you for your presentation. What is the maximum amount of energy that can be absorbed? Is the velocities allowed? And then LVI or HVI?
Yeah, that's a very good question. Actually, this is the results that is currently missing. In our paper, I just want to show a proof of concept, like we are able to introduce these sacrificial bonds in the engineering structure to achieve this high energy dissipation behavior, but we didn't systematically investigate how high velocity the material can handle, or how high energy the material can handle. And yeah, for the specific specimen that I made, I tested also under static loading. The maximum is around 5 or 6 joule, and then I tested at 5 joule under the impact energy of 5 joule under the falling dart impact tester. I think this is pretty much the limit of the current design. But by changing the design, and also it's related with, even though I'm using a film, but actually under impact, there are only those fibers, like 3 fibers along each direction, which is along the way of the falling dart will be actually functioning to resist the penetration of the dart. Actually, if we are able to increase the fiber density, or just to change, also depends on the size of the falling dart, we can of course increase the energy, total energy absorption of this composite. Yes.
Perfect, thank you. So we have also people that they raised their hands. So we have Zainab Grafti.
Yeah, hi. Thank you for your presentation, Shibo. So I had a question about the shape of the fibers. So from what I understood of the presentation, you can control the shape of the fibers by controlling the velocity of the extruder. So is there any interest in using, let's say, alternating fibers instead of coiled fibers, for example?
Yes. So basically, in our composite project, we choose to use alternating fiber. It's just because that the distance between each loop in this alternating fiber is larger than the coating fiber. So that's why that makes it easier for us to make this 2-layer fabric. If we use the coating fibers, actually the distance between each loop is much closer, and we have no problem printing the first layer. But when we print the second layer, because the first layer it created this non-flat surface, so the deposition of the second layer coating fiber will be much disturbed. We wouldn't have this regular coating fiber, or we wouldn't even have the sacrificial bonds. So that will lead to the difference in the mechanical properties between these 2 layers. That means that only along one direction the fiber is actually functioning, the sacrificial bonds is actually functioning, but along the other direction almost there's no sacrificial bonds, and that's not what we want in this kind of application. So that's why I chose alternating fiber. But there exists a bunch of studies of this instability deposition process, and it's basically the thing is that by changing the ratio between the velocities, not only the pattern was changed, but also the frequency. I mean, the wavelength of this pattern is constantly changing. Yeah, this is actually very interesting.
Perfect.
Great, thank you.
Thank you. So next we have Marie-Josée Potvin.
Hello, I'm Dr. Potvin from the Canadian Space Agency. This was a very interesting talk. Thank you. Have you thought, so if I understand well, so far you're printing 1 layer of it and then you're using it as a net, some sort of a net to catch objects. But have you given thoughts into printing several layers of it, one on top of the other, to form like a thick material at the end, but that would have some structural properties, but also some bending capacities?
Yes. To make multi-layer structures, it's possible to make multi-layer. Like here we have 1 layer of the film with a thickness of 1.5 millimeter. We can simply stack them up to make a multi-layer structure. But if we just want to increase the thickness, let's say I only have 1 fiber fabric here. If I want to increase the thickness, let's say not 1.5 millimeter, but 10 millimeter, but actually this, if we make it that thick, the mechanism won't work, because the material actually, here we would like to have a strong fabric and a weak matrix material. But if we make the thickness ratio much higher, so that the apparent strength of the composite of the matrix material is actually higher than the fabric, so the fabric will actually break after the sacrificial bonds wouldn't be able to be broken inside the matrix, because the containment of the matrix is so strong. It couldn't, so the fiber just breaks by itself. So that's why I say that we couldn't make it much thicker, but it's possible that we can make it multi-layer. And it's even possible, like with the same thickness, here we use a thickness of 1.5 millimeter. It's even possible, here you can see we put 2 fiber fabric, 1 straight fiber, 1 alternate fiber. Of course, we can try to squeeze 2 layer or even more layers of alternating fabric inside this one thin composite film. And that's also a possible direction to go.
Thank you.
Thank you.
Perfect. So we have another question under the chat. Thanks for so it's from Farzin Askari Arapadash. Okay, sorry if I'm pronouncing it incorrectly. So thanks for the presentation. How this method can beat the conventional non-woven toughening interlayers. Is its performance better than the non-woven mats?
Thank you for the question. Actually, that's the kind of question that we received when we submit this paper to the scientific journals. That's actually, this is the kind of results that is currently missing in our research. We didn't really compare this new fabric that we developed to conventional non-woven fabric material that you are speaking of. Actually, yes, right now I can only say that I don't know. Probably it's weaker because this is just a first proof of concept, and the material here is just polycarbonate and PDMS. And for sure, if we can use this design methodology by using other materials, stronger materials, with the right combination of the material properties between the fiber and the matrix to achieve this kind of behavior, I think it's possible that we can beat conventional materials in terms of impact absorption.
Perfect, thank you. So a question from Edu Ruiz. Would it be possible to combine this technology with traditional composites as an extra layer for higher energy absorption?
Yes, thanks for the question. That's actually a good direction to go. It's absolutely possible just to use this, because as also you already mentioned, the current film is quite flexible. It doesn't have too much bending rigidity, which is much required in engineering materials. And of course, we can integrate this soft impact absorbing film with conventional engineering structures to act like a protection layer and to increase the general impact absorption behavior of engineering materials. And yes, that's a good way to go.
Perfect, thank you. So we have been doing almost 12 minutes Q&A. It's great that we have a lot of interest. Maybe we have time for maybe two more questions. If there are any questions, you can just raise your hand or put it under the chat. I have myself a few questions. So I just wanted to ask one, which is regarding what you call fibers. So you're extruding polycarbonate, as you said, which is pure polymer. We know at the end, it has some anisotropy that when we 3D print, and so it's not an anisotropy material, it's in the structure. But why do you call it fiber?
Oh, this is a terminology, because actually we are not in the field of making traditional fibers. So because it's a fiber thread, so that's why we call it fiber. I'm not sure what's the professional terminology for, like, in the field of non-woven or woven fabric field. How you define this, I don't know.
Sure. Yeah, and maybe do you think, like, because when we are talking about 3D printing, we have fiber, pure polymers, and then we add short fibers to it to make it stronger. We can even have continuous fibers. But what do you think will be the performance of those? Like, instead of pure polycarbonate, if you have short carbon fiber reinforced polycarbonate, let's say.
Yeah, I got a question. Actually, we did that. That's a very good question. So here we are only extruding pure polymer. Actually, if we are talking about fiber, in composite materials, mainly that's the filler, the fiber filler that we added into this thermoplastic, so that it's a kind of nano composite. We can add carbon fibers or glass fibers into this material. Actually, we collaborated with a research group in Germany because they have a continuous fiber extrusion FDM 3D printer, where they pregnant the polypropylene, the thermoplastic, around one continuous glass fiber. So that's a continuous glass fiber, continuous fiber reinforcement. So we use that FDM machine actually to try to create this similar pattern, cooling pattern. But actually, it was more complicated than we thought, because here, in order to take advantage of this instability of this molten polymer, we have to have high viscosity. I mean, we have to have the viscous behavior of the material. So we have to use high temperature so it can coil on itself. But there's a problem if we use continuous fiber extrusion system. That is, when the material is the viscous behavior with a high temperature, the polymer will flow, and the fiber inside the fiber will try to expand, and this actually makes the instability disappear. So it more acts as a elastic body. So we tried this, so we couldn't have a very good instability deposition behavior. And also we tried short fiber reinforced 3D printing filaments, that those commercial ones, that carbon fiber reinforced thermoplastic fibers. And actually, even though, because I think for normal FDM 3D printing of those short fiber reinforced thermoplastics, you can increase the stiffness, of course, and the strength of the material. But in our case, we need a large scale deformation of the fiber or during the unfolding process. Actually, so if we try to use the short fiber reinforced 3D printing filaments, but after we create, there will be no problem creating this structure. But when we do the mechanical test, because it's very rigid, but it's also it's very brittle especially in terms of bending. So it can just breaks prematurely. So that's why we choose polycarbonate here. Yeah.
Thank you. It was great. So I see one last question, Gavin.
Hello there. Yeah, very nice presentation. It pretty much opened up a whole new world.
Thank you.
From the perspective of functionality speaking. So I have a question about transparency. So how important is this property from the perspective, like when you apply it, when you use it as the space net, for example?
Yes, the transparency is just that during the development, we came up with this idea to make it transparent so that we can create multifunctional composite materials, especially for the windshield materials, let's say on the airplane or construction windows. But it's not necessary to make it transparent. We can totally go non-transparent, like the traditional engineering materials or the contaminant material on the turbine engine. It doesn't have to be transparent. So, but we are still able to use this design methodology to achieve high energy dissipation.
Right, but if it functions as a windshield or a shield for turbine engine, it will also require to be structural, correct?
Yeah, exactly.
Okay.
That's why I say that the current product that we have here is kind of flexible. It lack a bending rigidity. Either we can use it together with traditional materials, engineering materials on those kind of structures to use that extra protection layer, or we can totally change the material components in our system, try to increase the bending rigidity.
Nice. I like the number of possibilities there. Also, another question is, what wavelength did you match your printed strands and the matrix, the refractive indices?
You mean which wavelengths of the light?
That's right.
Yes, for all the data I show here is at the wavelength of 589 nanometer, but you also see from these plots here, we test within the range of visible light.
Okay. Okay. Thank you.
Thank you.
Thank you, Shibuzo. It was very great presentation. Well done. I'm sure everybody enjoyed it. And thank you all for attending our Engineers Life event. And we'll have our next event in June. So just check always our LinkedIn page and you'll see the information there as well. Again, it was great to see you all and have a great day.
Thank you.
Bye.
Thank you very much, everyone. Take care.
Bye.